All right, 12 o'clock. Good afternoon, everyone. Let's get started. How's everyone doing? Yeah, morning. I'd say technically it's afternoon, but it's not important. Decent, great, more or less alive. I kind of feel the same. Excited and pumped for the exam. Well, we'll try to make it uh, fairly easy, or at least short. I don't know. Easy is a very hard thing to define. 5 questions? I was thinking about 3 questions. A 20-minute exam with 1 question. Well, you're going to have 3 questions and a 110-minute exam. 3 questions is terrifying? Really? Why? I thought the fewer, the easier. The better, the shorter. How many parts per question? Well, I know that's another question, but hopefully not too bad. So I'm actually thinking we have yeah, let me yeah, mess up 1 question, 66%. That's true. The fewer, the harder the questions, it seems. All right, I will do my best not to overcomplicate the questions, or to make them similar to the questions in the practice set. Make extra credit, please. Okay, so you are saying like 4 questions, and then after the fact declare one of them extra credit. Is that something that you folks would like? Okay. All right, let's do that. No issues. Yeah, so 3 questions and 1 extra credit. Sold. But as before, you will not know which question is extra credit. So, because I want people to try all 4 questions and not just skipping one because they feel intimidated by this extra credit. So extra credit would not imply that it's an extra hard question. All right, so let's do that then. No worries. And so let me start sharing something so that you don't get bored. Someone is asking how I am doing. Thank you for asking. I'm doing quite all right. A little overwhelmed by all the, exams that I have to write, because the exams you have to take, those are the exams I have to write. And if you think I'm enjoying writing them, 7 exams over the course of 1 semester, you are very wrong. So, all right, and I'm just reorganizing my windows as usual. So hopefully all our panelists are here. Please answer their test questions to make sure that I see you here. And I still wasn't able to update their points for being panelists. I apologize for that. Someone sent me an email asking about that. So yeah, I'm behind. I'm hoping to catch up. I have all the data saved, so don't worry. You will get your points. So if you were present in the lecture in which you were a panelist, and if you answered questions, then you will get your 0.25 of a point. So that's nothing to worry about it really. It just I need a little bit more time to get this done. And yeah, panelists, please do not, when you are done, do not end the meeting for everyone. Okay, because when you do that, since you are host, it basically kind of kicks everyone out of that meeting. So last time, one of the panelists ended the meeting for all, and I was cut out in the middle of a sentence. So please, just leave the meeting when you're done, but do not select in Webex end the meeting for everyone, because I wasn't able to save their chat from last lecture. Okay. And But will PSoft next year be run similarly to this class? Well, what do you mean similarly? If you specify what you mean by similarly to this class, then I probably would be able to answer your question about PSoft. Are there going to be exams? Yes. Are there going to be homework assignments? Yes. There will be also quizzes in PSoft. So I don't know if you take it as similarly or not similarly. Lectures in PSoft are going to be pre-recorded and shared with students just as videos. So that would be different. All right. So in any case, right, if you want to kind of make your question a little bit more specific, hopefully I can answer in more detail if you want. Okay, well, there's one lecture poll today, but there's another one from our TAs. Remember, all polls are counted towards our earn late days incentive, and I think we have close to 70 polls already. So that's what 4 additional lay days, right? That someone could have earned if I did my math correctly, and a little bit over 4. But so hopefully by there, in a few lectures, we can probably get to 5 extra lay days, and that would mean that a person who attended and got all those polls correct would end up with like 8 late days, which is way more than in any other CS classes that I know of, right? So to the best of my knowledge, typical late days allowance in a typical CS class is like 3, 4, maybe 5 late days. So I don't think there are any classes that offer significantly more late days. So I believe we are actually doing better than in that respect than other classes. But if you disagree, please let me know. All right, and so yeah, our first poll today is on homework 6 deadline, and I was just thinking that our original plan was to have that homework due before their Thanksgiving break on Tuesday night, and I know that Monday and Tuesday next week are officially just regular days. They're not no classes days, but I know in real life many people would be just living to go home, or it's a weird week. It's a short week, so I thought it might be beneficial to the students if we move the deadline for that homework to the following Monday. Okay, so we cannot have any deadlines on during the break, obviously. So the next the next regular day would be Monday. Wait, this Paul is asking us for vote on the deadline extension. Yes. Well, almost a week, yeah, because of the Thanksgiving break, and then I realized that homework 7 is going to be it's going to be, well, I can still post homework 7 um, on Tuesday before their Thanksgiving break, so that if anyone is ready to start on homework 7, they have they're able to do that. But yeah, if you use all the time for homework 6 and only submit it on Monday, then you're gonna have 1 week and 1 day, I think, for homework 7. And then the project is going to be due that week. That is true. So if if you take no action and all their latest all the last assignments in project due are going to pile up for the last week of classes for you, that would be true. Can we get a poll on the review session tonight? I'm guessing it will be yeah. So usually, and I responded that there was a question on the submittee forum. So typically, people ask me if I will be doing, if I want to do a review session like the Friday before, and I don't think it happened last Friday. At least I didn't notice anything in the chat, so I was kind of assuming that since this material is like we don't have a lot, people were not really interested. But then it turned out that some people were still interested in in running a review session tonight with me. And it's kind of last minute, so I don't think it really makes any sense to ask people to vote their for the preferred date and time, because as far as I can see, we only have two options: 8 to 10 tonight or 8 o'clock in the morning tomorrow. And I kind of suspect that most people are not big fans of doing anything at 8 o'clock in the morning. And me including, by the way. I could do that, of course, but it doesn't mean that that would be my first option. So if you folks need a review session, let's do it tonight at 8 o'clock in their late 8 o'clock at night, 8 p.m. Would that work for all people who wanted to attend? Okay, cool. And I'm just quickly looking through their. All right, 8 to 10 p.m. is ideal. All right, quiz 6 grades. Quiz 6. Did you mean test 6? But test 6 is tomorrow. So test 5 grades, if that's what you meant, is almost graded. So TAs are done, and TAs and mentors are done, and I just need to review the grades, probably make some adjustments, and then since now we have a review session 8 to 10, I don't think I'd be able to do it tonight, because I still have to take care of their test itself and do their seat assignments and write the test itself. But I will definitely make it available to you before the test. So again, hopefully tonight, but more likely tomorrow early afternoon, you should have their grades for test 5 available to you. Okay, and improve their deadline for homework 6, but you send out periodic panic emails to remind us of our impending project deadline. Yeah, so I'm trying to keep their number of automatic emails or mass emails that I'm sending to the minimum, because some students already complain that they're getting too much, right? So I'm sure you can just get into the habit of checking submittee. Oh, by the way, can you folks see my submittee window? Okay, so if I understand correctly, if you do this, interesting. Was there interesting? I thought there was a new feature on Submitted that is not officially published, but you could access it through the direct URL, and that is called Calendar. And I swear I tried it once and it worked. So let me see if maybe I can do it here from my student account. No, maybe they took it out. Oh, okay. So they fixed it. Yeah. All right. So then never mind, because I found that calendar to be extremely useful, right? Because it shows you all the deadlines for all your courses that are on Submidi. And so I can't wait for this feature to be actually available. So, and it was. Yeah, it was a feature, but it was available through a direct URL. And someone is saying they kind of closed that door, so I don't think you can now access that feature before they are ready to release it. Oh, you can. So it just yeah, I recall it was a calendar. Does it work? And it just need. Okay, it does work. Yes. So thank you. Yeah, you just had to do the direct URL correctly without the course and the semester. Just submit says RPI edu calendar. Cool. So hopefully. Yeah, it makes sense. Yeah, since it's for all classes, you don't specify the course number. All right, cool. So yeah, if you want to to keep track of all your deadlines, then I think this calendar is a very useful feature. So it's not officially released, but now we know how to access it. So yeah, please use it. Hopefully it's gonna help you. All right. Any MIPS on exam 6? Well, let's look at exam 6, at test 6. And so I think there are three major topics. One is sequential circuits, so flip-flops, latches, memory, all that stuff. So this is one big bucket. And then the other one is improving ALU, which is basically carry look ahead stuff. And then, of course, the topic from chapter 4, which is simple data path, right? So non-pipeline data path and everything related to it. So I think there are three major topics. So definitely expect one question from each of those topics. And yeah, I don't think there's really anything related to writing MIPS on this upcoming test. So yeah, I'm willing to say no MIPS writing on exam 6. We might still show you some MIPS code and ask questions about it, but no, you won't be asked to write any MIPS on this upcoming test. Whether for good or for worse, I don't know. Do most of you like MIPS, writing MIPS or not? Or yes, but not on the exam? If I had to guess, that would probably be my answer. Are we expected to calculate the delays for a circuit? Yes. So delays latency is definitely going to be in one of the questions on the exam. So are we writing C? I don't know. As I told you, I haven't written their exam yet. So, but based on the topics, I don't think it's very likely. Writing C. It because for sequential circuits, most likely the question will be similar to one on the practice test, where we give you some circuit and we ask you to analyze it and you know show us their timing diagram and the delays. So it's very similar to the question with that JK flip-flop from the practice set. So of course the circuit is going to be different, but the type of their question is going to be very similar. Improving ALU, this is carry look ahead. This is, again, we will probably ask you to, implement carry look ahead or write formulas for all those generate and propagate signals. So it's, yeah, I don't see how, it, I would be able to fit a C programming question in that topic. And finally, the question on data paths, again, it's mostly diagrams. So we will, either ask you to synthesize a part of the diagram, like we give you, a diagram that is incomplete and ask to complete it, or we give you a broken diagram and ask you to fix it, or we ask you, about latencies, like we give you the diagram and we ask you to compute, the amount of time it takes for certain instruction to execute given the latencies of each of the components, something along those lines. So yeah, I don't really see any room for MIPS writing MIPS code or writing C code. Okay, and yeah, hand cramps for writing MIPS by hand. Okay, so can we just make circuits during the exam? Well, it might happen. But you will see the previous test results soon, and many people did not do well on designing the ALU, which was basically just draw your diagrams. So amazingly, I thought the class would do much better on that question from the previous test. So drawing circuits does not necessarily mean it's an easy question. All right, will we expect it to have carry look ahead on the final project? I don't think so. I don't recall anything related to look at, well, but yeah, check their PDF. If it doesn't say anything about carry look ahead, then the answer is no. Okay, and Yeah, and I'm just trying to catch up with the chat, and I know I'm spending probably way too much time on this, but I feel it's important to address the issues that you folks have. Okay, we have no practice drawing circuits. We do bad drawing circuits. All right, you can practice drawing circuits, right? And you don't have to wait my, practice problems to do that. You can, and I mentioned it to, several people already. There are exercises at the end of your textbook, and they are the same in Zybooks. All right, so every chapter and every appendix has their exercises that you are more than welcome to use for practice. And then if you're lucky and you solve the problem from the exercises section of the chapter that I happened to include in the exam or in the homework, then you are all gold, right? Because you've already solved it. Okay, drawing ALU was the last problem, and I think most people do that. Yeah, so that's that. That is a very valid point. Please, when you receive your test, look at their look at all the problems and try to kind of estimate your time correctly. And if you see that one problem is long and it's 25 points, and the other problem is shorter, you can probably do it faster and it's the same 25 points. Do the shorter problem first, because if you run out of time on a longer problem, chances are you would still get plenty of partial credit. But if you spent you know 3 minutes on the last problem that is 25 points and you don't do a good job because you just ran out of time, it doesn't matter that your first problem was perfect and you got full score. You would lose a lot on that last problem. So it's an optimization problem. So you are as computer scientists or other closely related majors, you should be able to kind of think of a test as an optimization problem. So how do I solve the problems on the test to maximize my grade? Okay, can we do the ALU question right now? It might help us understand the ALU a bit more. So I'm willing to do their, so I assume you refer to the ALU problem from the test. Yes, we can certainly do that. But since we are holding this review session, I think it belongs there. We still have our new material to cover about pipelining today. So I recommend that we talk about the ALU from the previous exam in our review session tonight. Does that sound reasonable? Okay, and so I will post an announcement about the review session. So this has been decided and done. So practice problems solutions. I have a draft. I will need to finish it. I will try to finish it before the review session, but if not, then I will finish it right after. So I think I have 4 or 5 out of 6. Right? Was it 6 problems? So I think I have 4 or 5 solutions already written. I just need to finish the remaining ones. So today's material, no, is not going to be on the exam. Yes, and questions like that, please put them in the Q&A. We want to keep our panelists busy. All right, so for test 5 grades, I mentioned they're going to be released before test 6. Test 6 is tomorrow, so 3 major topics, right? So I would definitely concentrate on these 3 major topics. Sequential circuits, memory latches, flip-flops, ALU, advanced ALU, which basically means carry look ahead. That's a major thing that was not included in the previous test. And a non-pipelined processor. That is our latest topic. That's pretty much it. And then, so homework 6. All right, the voting is in progress. So I will see what people, typically think, and I will just go with a majority vote. If anyone, and at the same time, I don't want to discount any voices, even if they're the minority. So if anyone believes that moving the deadline would put them at a significant disadvantage, then just send me an email saying that no, we should not do that. All right. So I want to make sure that all concerns are heard. All right. So project next thing. So it has been posted, obviously, and you know, several days ago we already discussed it. And the most important thing for now is to get yourselves grouped. Hopefully, most people already, have their groups. And some people were asking me if I could increase their group size to 5 because the original limit was 4 people per group, and I cannot do this for just one individual group, and it wouldn't be fair. So I decided to increase the group size to 5 to the entire class. So if you want to have an additional person in the group, or if you haven't formed the group, then of course you are welcome. Anyone is welcome to form a group of up to 5 people. Okay. And of course you don't have to. All right, so the difficulty is not going to increase, right? So the project handout is what it was, and if you go for a large group, hopefully it helps you have a slightly less load on each person in the group. So I know many people were kind of astonished by my estimate of their commitment that I think the project would take. So, and like I said last time, it's just my estimate. I can be way off. I really have no idea. Maybe I shouldn't have said anything. So, I almost regret giving you a specific number of hours. But in any case, with more people, with 5 people, hopefully that helps a little bit with that aspect as well, so that each person will have a slightly less load now now that we allow larger groups. So yes, and fairly recently, Submiti um, got a new feature that now allows people to give their group, their team a name. So please, it's optional. You don't have to do that, but there were some very cool names already that I noticed. So some of them are listed here. Data decimators. I kind of like that. And me and the boys, that's a funny one. Or if you are not very creative, you can just go with a group, right? How about it? Right. So, and I'm thinking like, we can probably just have, once all the groups are formed, we can probably have a poll for their best group name. All right. So if we win the poll, can we get extra credit? I don't know. Let me think about it. I'm tempted to say no. I don't think it would be appropriate, but I'll think about it. All right. So just remember that project groups have to be declared by their end of the day 11:59 EST this Friday, this coming Friday. Okay, if you don't declare your group, then you're just going to be doing all the work by yourself, solo. And I strongly recommend against it. So please use Submiti Forum. Please use this chat during the lecture. Please use Discord. I know people. I know some students. I think started like a channel to search for team members. So on Discord. So use all those resources to find your team, or make a team with someone else. Right? It's your responsibility. And this kind of I won't be able to help you with this because I cannot decide who you want to work with. Okay, so please just do it yourself. All right, and all right. Yeah, one thing about homework 6 that I wanted to mention. So one student, and kudos to that person, brought up a potential typo in textbook problem 4.5. So, and that student came to me in office hours yesterday, and I don't know if that person is in the lecture right now. But if you are, thank you for bringing this up. So I told you that it's not an issue, but then I was thinking more about it, and I need to investigate further. It might be a typo that actually prevents students from solving this problem correctly. So I will look into that further. It's once again problem 4.5, and if I find that it is a typo, then I will of course share how this typo should be fixed. Okay, and if I don't say anything, then it means that there is nothing wrong with this problem. But I'm investigating this, so just bear with me on problem 4.5. Everything else I don't think is affected. All right, and with that, so past polls, let's quickly look at them and see where we are and what the correct solutions are, and then we quickly switch to our pipelining thing. Are there more mini polls planned for the pipeline lecture today? No, I don't think I have anything ready. So yeah, our goal was to have 2 polls per lecture or more. So I think with this being 22nd lecture, and we started with like lecture 5, I think that this whole polling incentive. So with even if we count all lectures, 22, 2 polls per lecture is 44, and I think we are currently at 69. Okay, so you can see the URL is the ID of the latest poll is 69. So I think we are doing good. Okay, for homework extension, Paul, yeah, I don't want to show the results while voting is in progress, because that would be affecting people who haven't voted yet. So I will, once their polls are closed, I will definitely share the results with you. All right, and so yeah, we. Let me see. Did we go over lecture 18, Paul? I don't think so. So we can do that now if you don't mind. All right. So lecture 18, poll 1, a latch is level triggered with a flip, while a flip-flop is edge triggered. So I believe this is the correct answer. And let me actually have both windows open at the same time so that we can. Oops, that's not the right poll. So that we can double check to make sure that my answers are correct. 18.1. That's not 18.1. This is 57. This is 57. 18. Interesting. No, okay, so it's oh, okay, I see what my problem is. So it's my problem. I have 2 lecture 18 poll 1. Sorry about that. So that that one was probably supposed to be some other lecture. That would be my guess. All right, so let's start with this 18 poll 1. All right, so that was the question about their associativity law that doesn't seem to hold in the associativity slide above. So that is actually one of the slides that is included in the upcoming test. So I'm glad we are reviewing this poll. So, and their answer is due to limited precision. So, to remind you of some context, when we are adding 2 values, then we lose precision, and the result is no different than one of the operands. And that loss of precision is something that cannot be recovered when we perform our second operation. So I believe that should be the correct answer, and it is. Okay, so then our next poll, 58. How can we further rearrange this expression to isolate CI? So this is another question related to carry look ahead, and the correct answer is apply commutative law twice and then apply distributive law. And so that is the majority vote as well. So I agree with students on this one. All right, so then 59. All right, so that was just a survey on their time of their additional Q&A session. So number 60, that was another poll, so not really interesting. So, and this one was on, okay, the difference between the latch and the flip-flop. So this is number 61. So this is just terminology, but, you know, still important. And their correct answer is latch is level triggered, excuse me, while flip-flop is edge triggered. And I agree with the majority vote here as well. 62. Here we had the question about how many bits would be the output of instruction bus in their instruction memory component on the slide that we were reviewing, and I agree. Of course, it's 32 bits, right? All our instructions are 32 bits, so the answer would be 32, and hopefully this is the correct answer that I have marked on submittee. All right, and then 63, and that was just a survey on homework, on the previous homework extension. 60, was it 63? Yes, it was 63, so now 64. All right, what is the maximum number of different operations supported by the ALU on slide R format instructions? And so we have the majority vote of 16, so let's see what my answer is, and it is 16. So that should be pretty straightforward because you just look at the multiplexer with a number of bits in their OP bus, right? And then, if it's 4 bits, then, just 2 to the 4th, 16. Okay, so that was that, and then 65. All right, why do we need shift left 2 on slide branch instructions? And yes, so this one was kind of interesting. So let's look at it. And the correct answer is just to account for the fact that instructions are 32 bits long, 32 bits, whatever, just a typo. All right, so that so that happens to be not what the majority of students voted for, right? In fact, relatively few students voted for this. So the answer is, shift left is just because any address in memory of an instruction, right, has to, instructions are 32 bits long, so they take 4 bytes in memory. That's why when we are making, or when we want to have an address that would point to the instruction, that address has to point to a word boundary. And this is a direct consequence of the fact that instructions are 32 bits long. Okay, so we want our addresses in instruction memory to be like 0, 4, 8, 12, 16, and so forth. And this is exactly why we need that shift left 2, because obviously they're least significant 2 bits, they are always going to be 0 in any memory address that refers to the address of an instruction. And that's why we don't need to store those zeros, right? They are sort of, if you want an analogy, it's like a hidden bit in IEEE 754. So that means we don't store them, but when we prepare the address, the actual address, we have to account for them. And we do that by shifting left by 2 so that we get those 2 least significant zeros back in place. All right, so And yeah, this answer that most students selected really is not true, because PC plus 4 would be automatically taken care of by our adder, right? So we don't need to compensate for that, especially, it's not really compensating. We are not adding or subtracting 4. We are multiplying by 4 with our shift left 2 thing, okay? So that was another hint that was supposed to kind of tell you that this is not the correct option. All right, and then 66 was this. And yeah, this is just nothing really, not a new material. So we take the value of S3, subtract 32, and this is their, yeah, but we had to refresh it because we were talking about their load word data, the data path, and how which components would be used for load word instruction in this data path. And people tend to forget how different instructions work. So that was a little refresher here. All right, and so 66 was it? All right, so and yeah, so we just compute their address first, S3, the value of S3 minus 32, and then we use that to access memory. That's why it's M, and then in brackets we have their effective address, the effective address that we computed from the base address in S3 and our offset negative 30. Negative 32. So it looks like that's exactly the option that most people selected. All right, and yes, on the previous slide, on the previous lecture, this is pipelining. So the correct answer is false. All right, so the correct answer is indeed false, because it doesn't mean that any load would be done any faster than it would be in the sequential non-pipelined mode. So we are really not increasing the latency, we are increasing the throughput. So this slide, this question was hopefully to set you thinking about the differences between throughput and latency. All right, and so that was 67, and I think that's it. All right, and we are back to 68. Okay, this is today's, so we're not gonna go over. For rainbow grades, yes, I will update them once we post test 5 results. So that is before test 6 tomorrow, rainbow grades will be updated. All right, what slides are on the test? So I think we discussed it in the beginning of the lecture, not with the particular slide numbers, but with what material is going to be included, and it's also on the Submit forum. So if you want specific slide numbers, ask your question in the Q&A, and then one of the panelists will be able to give you specific titles of the slides, if it hasn't already been answered, because I'm looking at the Q&A and I think that there is a closely related question about the scope of test 6. All right, yes, and so finally, let's get back to our material. And so we were talking about, all right, it got screwed up a little, and I need to reposition. So we were talking about the pipelining and how it is a very common, a very popular method of increasing their throughput or executing things in a more efficient manner. So it's all about performance, it's all about efficiency, right? And so then there was that pop quiz, and so MIPS pipeline, right? Well, so now we see that what a pipeline is, right? So we need to determine what would be what their components that are part of the pipeline are. In our laundry analogy, our components were all the devices that we use to do our laundry, the washer, the dryer, and so forth. So we have to do something similar now in our MIPS in our processor, right? So in our MIPS processor. So if you think about it, then you can divide all the tasks that any instruction has to perform into 5 stages or 5 phases. So first we need to read the instruction from memory. So this is what is called um, uh, instruction fetch. Okay. Uh, right, where fetch is just a fancy word for read from or extract. And then we need to decode the instruction and read registers. So read register, register read, or read registers is pretty straightforward. We need to read all the arguments from the register files for instructions that do operate on register values. Instruction decode, on the other hand, is less straightforward, right? Because once we've read the instruction from the instruction memory, we already have the instruction word. So what does it mean to decode? As one example, think about all the control signals that you need to generate from your instruction, right? All those that we reviewed last time, reg, dst, mem, read, mem, write, all those, tons of control signals. And the way we generate them is by having some circuitry, having some gates that take different parts of the instruction word and produce those control signals. And of course, all those gates, they do not function, they do not work simultaneously, they do not work infinitely fast, so they have their own latencies. So instruction decode includes this process of generating all the control signals from their instruction word. That's why it's called decoding. And so then execute, obviously, we need to execute the operation. So it would be usually the job of an ALU, for example, to perform the addition, subtraction, or whatever operation we have from their instruction, or it can be calculating the address if it's, for example, a branch instruction. And then now we have mem and WB write back. So mem is memory access. This is only relevant to instructions that access memory, so load or store instructions, that is. And then write back is writing the result back to the register. This is only relevant for R-type instructions. Only those instructions write something into the register file. So from this list, you can see, you might say, well, not all instructions need all 5 stages, which is true. So for example, R-type instructions would not need the memory stage, right? Because they do not operate on any memory operands. On the other hand, for example, a load and store instructions would not need the write back stage because they are not writing, well, load does, but store, for example, does not write back into the register. And branch instructions do not write anything into the register file. So it's another example of instructions that do not really need this write back stage. But as we discussed before, one of the principles is that we want to make the common case fast. So we want to have a single set of stages that would accommodate all the instructions at once with a single schedule, right? With a single set of stages. So you see that that's the set that satisfies this requirement. So all instructions that we discussed will not need any additional stages. Any instruction that we have will be able to be executed using a subset of all those 5 stages. That means that we have to have all 5 stages. And if some instructions do not need some of them, well, that's too bad, but that's our design decision, right? So we have to design for the worst case with instruction that actually uses all those 5 stages, or all instructions together. They will require all 5 stages. All right, so how do we assess the performance of a pipeline? So let's run this quick example. So we assume that the time for stages is as follows. 100 picoseconds is to perform register access, read or write, doesn't matter. We here assume that it's the same, it's the same latency. So this is a register, file, read or write, and then 200 picoseconds for all other stages. And this is actually quite realistic. So we will assume this kind of ratio in many of our estimates, right? We will assume that reading register or writing a register happens about twice as fast as any other stage of the pipeline. So, and now we need to compare the pipeline data path with our simple non-pipeline single cycle data path. All right, so here is their table that shows this. So, and the table shows just for different instructions which stages we are going to need. So this is IF instruction fetch. This is instruction decode, which includes register read. This is execute. All right, so ALU operation, this is memory access, so it's MEM. Note that memory access is 200 picoseconds, right? So a shorter time, faster access is only for the register file, not our other memory. All right, and register write, it's write back. Okay, so and now we can look at their sum and we see, oh, really, we have this load word instruction that actually use all 5 stages. So that convinces us that, yeah, we have to have 5 stages. And then we just sum up all their, all their latencies for each of their phase, right? Register read and register write, again, we assume it's the same, 100 picoseconds, and then all the others are 200. And all other, well, at least all other instructions that we see in this table, they do not use all 5 stages. So, their total execution time would be less in a single cycle data path, right? Because, in a single cycle data path, we are not really, bound by any other limitations. We don't have anything pipelined, so we can say that, yeah, we can attempt to do this, to get the clock cycle shorter. Maybe we'll actually see that no, it's not going to happen. But our initial hope would be exactly this. So this is total. This total time is just a sum, right? So store word doesn't need to write back into the register, and therefore we can just sum up their latencies of the 4 stages that SW uses, and it sums up to 700. And we see that BQ is, for example, is even shorter. It's 500 picoseconds. So from this, you might be, next question would be, again, this is just for the single cycle, non-pipeline data path. Your job would be deciding on their clock period. And, another, so it's the same principle that we discussed before. We cannot make, I should say, do not want to make different clock periods for different instructions, right? So, and I just put here meaning that it's this stage is not used. So, we want things to be simple. We want our design to be simple, and that means that we want to have the same period for all instructions, which means that we have to go for the worst case, which is load word, which has 800 picoseconds. So our clock cycle, our period of our clock is going to be 800 picoseconds. And yes, the majority of instructions would not use this fully because they have stages that, they have hardware that they're not using for their execution. But at least we have to account for the worst case, which is LW, which uses all those, and it will, it will definitely require full 800 picoseconds, and we have to make our clock time, clock period time exactly that. All right, so let me see. Mem access is just finding where to put the commuted value for R format. No, mem access is accessing their memory, right? And memory is only accessed with load and store instructions. Load word, load double word, load byte, load half byte. right? So that's the memory access, right? This is to give you um, a reference point. When you define your data segment, right, this resides in memory. This is not part of the register file. R format instructions only operate on so R format is the format for R type instructions. If you look at their MIPS reference card, you will see that R format instruction. Yeah, it's like arithmetic and logic. So, you add and 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 OR and sub. All those are R format instructions because they have 3 registers. 2 registers that are read, which contain operands, and the 3rd register, which is written, which is the result of the operation. All right. Okay, so we are back to our pipeline performance. So for a single cycle, we have to go with a period of 800 picoseconds, obviously. And if we draw our, our timing of how instructions are executed, and this is a very common layout of how we show timing, right? So time, or T, will go down. You see the arrow goes down. So, you know, the stuff at the top happens earlier. The stuff at the very bottom is the most recent. So we first execute this instruction, then this instruction, and then this instruction, right? So time kind of goes down. And we see that, here, of course, time goes to the right. And we see that if at time 0 here, we started executing our first instruction, then it takes 800 picoseconds, and then 800 picoseconds for the next, and 800 picoseconds for the next. And even if not all load word instructions were load word instructions, but even if we had some other instructions, for example, the instructions that didn't have data access, right? It would not. So, for example, if there was no data access, right? If it were not a load word instruction, but let's say if it were an RTOP instruction, we would actually have the register right here. So technically, our instruction would be done executing in less than 800 picoseconds, and we know exactly what it would be. It would be 600 picoseconds, but the clock would still be the same, right? We would still have to, wait those 200 picoseconds before the third instruction, the next instruction, would start executing. So the clock is the same because otherwise it just becomes, it's just going to be a very, very obscure design of of our processor. It just complicates things tremendously. That's why we don't want to do this. It can be done, but we don't want to do this. All right, so what about pipeline thing? Here we have to select the clock cycle based on the duration of each individual phase, right? Because we are now basically, imagine like we take our single cycle and we kind of slice it into 5 stages. So the clock now is the time for one stage, not for one instruction, but for one stage that an instruction executes. And that means that we again have to come up with a worst case. So we see that some stages take 100 picoseconds, like here, register read and register write, but some stages take 200 picoseconds, like everything else. So we have to select our clock cycle to be 200 picoseconds for the pipelined version of the processor. Otherwise, we not going to be able to make it. Okay, so and that's exactly what we do. So now our clock cycle is 200 picoseconds, and we have some stages in particular. So this is instruction decode for the first instruction, right? And this would be write back for the first instruction. Okay, so we have some stages that would not use their clock cycle, completely, but it's fine. The same way it was fine previously that we had some instructions that would not use their clock cycle fully. All right, so that's why here you see that if you look at their execution time for, let's say, this instruction, okay, So what would be the execution time of this first instruction? Can someone tell me? And the execution time means from the start to the end, right? So one instruction fully, exactly, it's 1000 picoseconds, right? Because we have, and you can compute it because we have 5 stages times 200 PS each stage. So it's got to be 1000. So you might say, wait, what what is going on? Like, wait a minute, how come we switched to pipeline version and we actually lost their instruction execution time, right? Because previously each instruction would take only 800 to execute, but now each instruction is taking actually longer, 25% longer, 100 picoseconds to execute. Okay, so this is crazy. It looks like we're not actually improving anything. And the answer is yes, we're not improving their execution time of any given instruction. That is totally true. If anything, we are making it worse. But if we look at the throughput, we are quite a lot ahead of our single cycle non-pipeline version. Because if you look at their whole picture, even with these 3 instructions, how long does it take to execute these 3 instructions that are shown on this slide? From time 0 until the last instruction is fully done, is fully executed, how long is it going to take? Exactly, 1400, right? Because our third instruction will be done at this moment of time, right? So it is 1400. 200 and 200 is 400. And then this, for the last instruction, this is 1000, which we already discussed. So it's 1400. So now things are looking much better, right? If you think, oh, it took me 1400 to execute 3 instructions, oh, that's not too bad. That's actually much better, right? Because we have you know, on average per instruction, we have a much shorter time than 1000 or even 800, right? We have improved a lot. And this is the difference between latency, or the amount of time it takes to execute any given instruction, to the throughput, right? So here we are computing the average amount of time per instruction, and this is exactly what is called the throughput. And with 3 instructions, it may not be actually impressive, but then if we think about it, if we have more instructions, then if we look at at the tail end of our pipeline, we will see that, oh, one instruction is done in every, so let me use some other color, right? So first instruction is done at time 1000 here. Second instruction is done at time 1200. Third instruction is done at time 1400. And then we are going to get one instruction done at every 200 picoseconds. So effectively, our throughput would be 200 picoseconds on average per instruction, right? If we have sufficiently large number of instructions, so that this initial stage before 1000, before we started producing our instructions at this sustained rate of 200 of one instruction every 200 picoseconds, then if we have sufficiently large number of instructions that we can ignore this initial kind of start uploading their pipeline to the full period, then we can say, yeah, it's 200 picoseconds, we get a new instruction executed, done, completed, which of course is 4 times better than this, okay? And it's 5 times better than this, than 1000 picoseconds. All right, so remember the formula that we had, that roughly in the sustained mode, so we're circling back to this, right? So in the sustained mode, the speed up versus non-pipelined would be the number of stages. In that case, it was 4. In our case, with MIPS, it is 5, right? Because we see that it is 1000 in a non-pipelined versus 200, right? Which 200 picoseconds, which is exactly 5. The number of stages, 5, right? So it's not a coincidence. Of course, if you make an argument saying, well, but wait a minute, it's not a fair comparison. We are computing the speed up versus their, their pipelined time period. But if we didn't have a pipelined design to begin with, we could use 800 to execute any instructions. So the fair comparison, some might argue, would be actually 800 picoseconds divided by 200, right? So that we compare apples to apples. One option, no pipelining, and each instruction takes 800 picoseconds versus our pipelined design where each instruction in the sustained mode is only taking 200 picoseconds. So that would be 4, and 4 is obviously less than 5. And that is also true. And I would agree with those who say, well, this is their real speed up. This is their true speed up of pipelined design versus non-pipeline design. And it's less than the number of stages. Why? Because there's an important string attached here to this formula, right? This, okay. This string attached is here on the next slide. It is under the assumption that all stages are balanced. Are all stages balanced in our pipeline design? No, because we don't have all stages taking exactly the same amount of time, 200. We see that some stages take less, 100. So it's not balanced. And because of that, this lack of balance was not affecting us in the single cycle design. Note how this, here register takes register read, register write, they take exactly 100. We didn't have to extend this stage to 200, right? Because we didn't have pipeline. We were not concerned with making all stages the same length, the same latency, right? So the register read write was only contributing 100 towards the overall balance of their instruction execution time in this non-pipeline design. Whereas once we switched to a pipeline design, this register read, register write stage is still 100 picoseconds, but we have this, empty space. Well, it's not empty, but it's, their space, the time really not needed by register read write. So it's just wasted time when our register file is not doing anything, and that's the reason why we are not getting the maximum possible, theoretically possible speed up, right? The maximum theoretically possible would be 5. We are only getting 4 because of this lack of balance in all the stages. Okay, so if you change the numbers and say, all right, what if we had actually 200 here for register read and write, then of course we would change our numbers. So here instead of 100 we would have 200 and 200. Okay, and then the load word instruction would take 1000 picoseconds, and then we would get a 5, a speed up of 5 when we switch to pipeline version. Okay, so that would be then, of course, we would achieve the maximum speed up. Of course, it makes no sense, right? Because we, why would we want to make things slower just to achieve, a better speed up if we had to make it slower in to begin with, for our non-pipeline design. So that's why we, of course, not going to do this, right? But that explains why we are not why we are getting the speed up of 4, not the theoretical best speed up of 5. All right, what if you have to branch a jump? Wouldn't the next few instructions be executed? Again, no. They could have if we designed different time period for different instructions, right? Because obviously branch and especially jump can potentially be executed a lot faster than all other instructions. But we are designing so that all instructions have the same time clock, because otherwise, like as mentioned multiple times before, it makes the design extremely complicated if we have different clocks for different instructions. And that's why, yes, even the jump instruction that may take, only 1/3 of, 800 picoseconds in a non-pipeline design, it would still take, it would still be executed in the same clock cycle as other instructions. So it would still take 800 picoseconds. And if we switch it to pipeline design, yes, so we would not be able to get an instruction out of the pipeline in less than 200 picoseconds. So that's the minimum, right? So one instruction is done every 200 picoseconds, no matter what, even if the instruction can potentially be executed faster than that. So if you do S0 T1 T0 and then add T2 S0, all right. So yeah, you are looking ahead a little bit, and this is the ideal case, right? So this is when we do not have any, any bad dependencies between our data. Okay. Yeah, homework 6 early doer gang. But yeah, good job. So this is the ideal case, and everything we're going to discuss next is just going to be, south from there. It's just going to get worse and make our lives, miserable, because it's going to complicate things. So, and of course, the problem is, imagine here this instruction. So, imagine that it needs to, right? So this part, let me use yet another color. So imagine this part needs to read the register, okay? But that register is written by the previous instruction here. All right, so here is a problem, right? So we kind of, have to go back in time, right? So at time 600, well, at time 700, this instruction, and again, it's not going to be load word, so it's not the case shown here on the slide. It's another hypothetical case when instructions are different, and it may happen that this third instruction needs to read the register at time 700. That is only going to be done writing at time 1100. Okay, imagine it's the same register that the second instruction writes and the third instruction reads. Obviously, that ain't gonna happen, right? We cannot read the value before it was read the register before it was actually written by previous instruction, and that's a problem that is known as a hazard, and that we would either have to combat by using forwarding, or we have to give up and we have to stall our pipeline, basically to delay the instruction until the data that it needs is ready. All right. All right, so that's that. And someone is asking, why is it 800 over 200? Well, because it's 800 in the non-pipeline design that we get an instruction executed. So if you look, from the standpoint of the user, we get the first instruction done at 800, next done at 1600, and so forth. So one instruction is done every 800 picoseconds, and in a pipeline version, we have an instruction done every 200 picoseconds. So it's a speed up of 4. Yeah, a drop deadline has passed. Well, why would you want to drop such a wonderful class, right? Especially since you're almost done with it. Why register starts at 300 picoseconds, not 200 picoseconds? All right, that's a very legit question. So let me address it. So we have this. I want a different color. This one. So we have this 200 picosecond time slot that we know we only need 1/2 of to do register read or register write. So where do you and you have freedom in where within 200 you place this 100 piece. Okay, so for example, you could have done here like that, right? So you just do your read or write at in the first half of the clock cycle, or you could have done it here, right? So that you are doing your read or write in the second half of your clock cycle, or you could have done anything in between, like in the middle or something. And as we shall see, it's probably not going to be making much sense. Okay, why? Because here we are very fortunate to see that. Oh, okay, for this, right? So this is instruction decode, which means it's register, read, and write. So it's all register operations. So can we maybe somehow, take advantage of this fact? Let's see. What if we have two instructions, and we accept this option number 1, Roman numeral 1, right? So this is 1, where we perform the register operation, whether it's read or write, in the same part of our larger 200 picosecond cycle. Okay, so sounds good. And let me use red for read, and let me use orange for write. So that would be fine. Okay, there's nothing wrong with this. But if we have two instructions, one after another, that read and write the same register, then we would not be able to execute them next to each other. Okay, because they would have, this, register read is not going to be able to read the register because it is just written at the same time. So instead of doing this, we would have to sort of push our second instruction so that it's the other way around. So let me actually not read and write, but we need to swap them. So let me fix it real quick. There's my eraser. And I'm going to do. So this would be, the orange would be read, and then the red one would be write. Okay, so obviously, the top instruction, which happens first, should complete its write before the bottom instruction, which happens next, would be able to read this written value. Again, here the assumption that we're making is that read and write occur on the same register. If they occur on different registers, it's not a problem. If they happen for the same register, it's a problem, which causes us to sort of delay our read, the instruction that needs to read this register. So instead of doing it here in this clock cycle, right, we have to basically say, all right, we have to do it in the next clock cycle. And here we would read this value here, right? And then it's fine because the value was written here and it is read here. So we can, kind of show the dependency with an arrow. Okay, again, it's the same register. It only applies when it's the same register, because if it's different registers, it's not a problem. So, and if we attempt to do it without shifting in time the second instruction, it's not going to work, right? Because we do not have this value written by the time we want to read this value. So, and this is of course a data hazard, something that we are getting to start discussing. And so one thing that could make our life a little easier is strategically separate the read and write operations within their clock cycle. So instead of saying that we do whether it's a read or write into the register, we do it in the first half of the cycle, right? Because we can. We can say, all right, let's do the write in the first half of the cycle. So the write would happen here, and the read would happen in the second half of the cycle. Okay, we can totally do that because whether we are talking about read or write, they only take half of the cycle. They only take 100 out of 200 picoseconds. So we can totally do that. And then that would allow us to actually not waste the time in example like this one, right? So that is going to be our option number 3, right? 3 Roman numeral, right? 1 would be to do everything in the first half of the cycle. 2, it was this one, in the second half of the cycle, and 3 is to do a smart thing and write in the first half and read in the second half. And if we do this, option number 3, we see that in the example that we looked at, we won't have to move our instruction or delay our second instruction because it would be able to read the value written by their instruction in the same clock, by the previous instruction in the same clock cycle, because they are, they happen in different halves of their clock cycle. So we are good here, even if it's the same register. Is that making sense? Okay, cool. So we already talked about stages being balanced or not balanced. So if all stages have the exact same time, like 200, we call them balanced, and then we apply this formula, right? So time between instructions, basically, this means, how many picoseconds or whatever your time unit is, we get a new instruction completed. And then divided by the number of stages, that would be the time between instructions pipelined. All right, so like in our example, it would be 200 divided by 5, and that would be 200 if we had all stages the same 200 picoseconds. Excuse me. Which we know we don't in our example, so it's not balanced, and that's why the speed up is less. Remember, we have the speed up of 4, which is less than 5. All right, so, and as we have already seen, the speed up that we were getting was due to throughput, right? So we were not gaining anything in terms of the latency or the time a particular single instruction is executed. It actually went up, this time went up. So, from 800 to 1000 picoseconds. So it actually, in our example, turned out even worse. But the speed up in terms of the throughput is definitely visible, right? 4 times speed up is significant, right? It's not peanuts. It's something that is worth fighting for, and complicating the design of our pipeline. All right, so I don't know if you would agree or not, but yes, designing a pipelined data path would be significantly more complicated than our previous simple or non-pipelined data path. All right, so let's actually approach the design of the data path. So we know that all instructions are the same length, 32 bits in MIPS, which is a big advantage compared to x86, where instructions have various length, 1 to 17 bytes. It's a pretty big spread, and it makes things a lot more complicated. So luckily, we don't have that in MIPS. So we have very few and regular instruction formats. So there are just basically, by and large, there are 3 instruction formats, right? R, I, and jump. R format, I format, and jump. So that means that we can decode the instruction code and read registers in one step. So we can, so when we say the stage ID instruction decode, we say it's decode and read registers. So that can happen in one step, right? That can happen in one stage and take only one clock cycle. So we also have to worry about load and store addressing, but if we think about it, we can calculate the address in the third stage, so that would be the EX stage, execution stage, and then access memory, our data memory in the fourth stage, so we are good. All right, so no need to change anything. And then finally, some good news for us is that we have alignment of memory operands. So this is related to that poll that we just discussed, one of our older polls, right? So we know that all memory addresses, they end in 0, 4, 8, or C. So we are talking about instruction memory, of course, IM, instruction memory. Okay, so we can read an instruction in one clock cycle, because reading an instruction basically means just read 4 consecutive bytes, right? So here we have 4 consecutive bytes, and then 4 consecutive bytes, and then 4 consecutive bytes. So it can be done in one clock cycle, which is good news. So of course, bad news are hazards, and someone already asked a question that kind of led me to explain what the hazard is. So it's the situation that prevents the following instruction from proceeding or completing its execution because it doesn't have everything that it needs to proceed. So there are 3 types of hazards, and there is Roman numeral 1. So yeah, I know someone is making jokes, but I will try to pronounce it better. Roman numeral 1, Roman numeral 2, and Roman numeral 3. Okay, so structure hazards, they present a hazard when a required resource is busy. So, and that's why they're called structure or structural hazards. Imagine that you need ALU to compute their effective address, but the ALU is busy by another instruction that is computing, let's say, their value for the add instruction. So that would be an example of a structural hazard. And usually this is a design flaw, or it just, maybe not a flaw, maybe it was meant to be that way, but it's a design thing, and there's not much you can do about it. So structure hazards are related to the hardware that is not sufficient, right? We need probably to duplicate certain hardware so that we can proceed with several instructions, concurrently. All right, so that's the structure hazards. That's probably the hardest of all hazards, because there's not much we can do other than redesign our hardware and throw in more hardware resources to avoid structural hazards. All right, and how does the compiler know if a resource is busy? Well, the compiler doesn't know that, of course. The compiler generates their instructions, and then it's the job of their processor to perform instructions. So how do you know if a resource is busy? Well, in the simplest form, you don't, and that can cause you problems. For example, imagine, and I'm very bad at drawing things, but imagine this is your washer, okay? And that would be an equivalent of some hardware resource in our processor design. So how do you know if it's busy or not? How do you know if you can go ahead with your load of laundry or not? Anyone? If it's empty, how do you find out if it's empty or not? Well, wait for it to finish. How do you know? Yeah, open it, exactly. You can check, but if there is no glass window or glass door, you have to open it. Okay, so the most unsophisticated way of checking is to actually open and see if anything is there, right? But by opening the washer, if it is currently washing another load, is destructive. Okay, so of course, a modern machine would not let you open the door if there if it's still working on their, if it's still washing, right? But if you apply some you know engineering skills and overcome that protection, you can actually open it, right? So it would not do you any good. So it's like just throwing it in your laundry without really checking if it is available or not. And it's the same type with processors. So if you have, let's say, your instruction memory, and well, a better example would be actually, uh, let me say, this is your data and instruction memory. So I call it DIM, right? Data. Imagine you have a single memory, which contains both instructions and data, and you are attempting to read from it. Okay, so what would happen then? So here is your here's your time: 0, 200, 400, and you are attempting to read from this instruction, read the code for this instruction. So it's going to be instruction fetch, and then imagine that then a few cycles later, so this would be mem stage for the first instruction. You are going to write data to that memory, and again, this is a single memory, and some other instructions. So that would be the mem stage, and there's another instruction for which it's going to be the instruction fetch stage, but it's the same memory. So it's like one instruction is trying to read from the data memory, and it supplies the address it wants to read, and the other instruction is trying to fetch to read the instruction, of course, from a different address of the memory, but it's the same memory, and it only, unlike the register file, remember we discussed the difference between the register file and our common data memory is that register file can support simultaneous read and write from multiple addresses. So data memory has no such capability. It is only accepting one address, and it can either read or write from that single address. So that means that if we allow this, then we would have um, two instructions trying to supply different addresses to the same address bus. There's an address bus, there's an address bus here. And if we have two instructions trying to supply different things on the same bus, on the same wires, it's just not gonna work correctly. It's not gonna read any of those two correctly. So this is an example of a structural hazard. Okay, so every time you finish a cycle, you wait another entire cycle before you go each time. So the time it would take you to finish would be multiplied by 2, which would totally defeat the purpose of pipeline. Exactly. So hazards are not a pleasant thing. We don't want hazards, clearly, right? Because every time you have a hazard, if you have to delay their instruction, you delay it by at least one clock cycle. And in our examples earlier, the clock cycle was 200. So that means that you shift this instruction in time by 200 picoseconds, and that means that all subsequent instructions get shifted as well. So basically, you are effectively losing 200 picoseconds because of that hazards, at least, and maybe more. So we will see, right? So structural hazards, as we showed in this example, it's not much you can do about it rather than redesign your hardware and throw in more hardware. All right. Does the compiler take care of hazards? No, it shouldn't. It should be the responsibility of their processor, because we just cannot trust the compiler. What if it doesn't? What if it doesn't take care of their hazards? Then it would mean that our instructions are not processed correctly are not executed correctly by the processor. Would you buy a processor that relies on their software, on their compiler to work? And if their compiler is not doing a good job, your program would not execute at all? Probably not. You're not going to spend your money on such a processor. The important aspect, though, is, and since you mentioned the compiler can totally do some tricks to make sure that no or few hazards take place. So there are strategies for that, but it does not mean that the compiler would guarantee there are no hazards thing. Okay, it can try to, with their idea of, all right, if there are no hazards, then their efficiency would be better, the performance would be better. But if it doesn't care, or if it just doesn't pay any attention to hazards, your code should still be executed correctly. All the instructions should still be executed correctly by your processor. Maybe not in the most efficient manner, but still executed correctly. All right, so so we're not going to be talking too much about structural hazards, right? Because that would involve, their conversation about designing the hardware, which I feel many of you think that this class is too heavy with lower level hardware details to begin with already. So we mostly going to talk about these two types of hazards: data hazards and control hazards. So a data hazard is something that is related to the dependencies in data. So data hazard is when we need to wait for the previous instruction to complete its read or write operation, because our next instruction needs to read that data. And control hazard is something related to branching, right? So if we have a BQ, BNE, and deciding whether the branch is taken or not depends on their value produced by the previous instruction, we may not be able to make the decision on whether we take the branch or not until the previous instruction completes. So structural hazards, this is something we talked about. So for example, MIPS pipeline with a single memory where instructions and data are all in the same memory. So obviously load store requires data access, but also instruction fetch requires reading from that memory, and it cannot happen simultaneously if it's the same memory. Okay, and it's data memory, so it's not this register file that allows us to have access from with multiple addresses. So that would cause the pipeline to bubble, or to wait a little until, so that load store reads data or writes data in a different clock cycle from the instruction fetch. All right, so and that kind of brings us to the idea that to make our lives easier, we want our pipeline data path to insist that we have separate instruction and data memories. And there are ways around it. For one, you can have actually just separate instruction data caches, but we're not going to talk about this, right? So we assume for this chapter, we assume that we just have separate instruction data memories. All right, data hazards. So this is what you're gonna need for homework 6. So here's an example of a data hazard. So imagine these two instructions executing one after another, and this instruction add writes to S0, and then the next instruction, the following instruction sub reads from S0, right? So this is write, this is read, and now we draw this diagram that shows which resources are used when. So their convention here, and it's the same convention that is used in the textbook and in Zybooks in all the figures, is if one part of their component is is grayed, like this part, you see it's in dark gray, it means that it means that this component is red. And if the right part is great, it means that this component is written. Okay? So for add instruction, we see that we read the instruction memory, and so that's why the right half is great. And then eventually at the 5th stage, we're going to be writing back to this register. So that's why it's the left half of the component is grayed. Okay, so that is their convention. And then you see that, like here, can you see this is solid, and this is dashed line. So dashed line means that really this stage only needs half of the cycle. So we see that the only component for which we can do half of the cycle is our register file, and that's why ID instruction decode have this dashed line, meaning that, oh, this memory, this register file is only going to be used for 100 picoseconds, right? So, and we are going to use their second half of their cycle to read this, okay? And this is reading, hence their shading of the right part. Here it's the same. We're gonna have their same register file. So it only takes 100 picoseconds to write to it, and we are writing. That's why we're using we shade the left part of it, and we know that it's going to be done in the first half of the clock cycle. So it's going to be done here. Writing happens here, and reading will happen here in the second half of the clock cycle. All right. So now this first instruction, right? The way to read those diagrams is actually one clock cycle at a time, right? So this diagram shows multiple clock cycles, right? Just as a reminder, this is what we call a clock cycle, okay? And we look at them one clock cycle at a time. So this first clock cycle, what happens? Instruction fetch for the first instruction. Next clock cycle, what happens? Instruction decode for the first instruction when we read T0, T1. Okay, and then normally we would like to start fetching their instruction next, right? This instruction, but we know that we cannot do this. Why not? Well, if we imagine us doing their instruction, doing the instruction fetch here, then for the second instruction, for our sub instruction, then instruction decode would happen here in this third clock cycle. And it means that we should have S0 ready, but we don't have it ready because it hasn't even been computed, let alone written by the first instruction. That's why we have to insert what is known as a bubble. So we have to stall the pipeline and delay our next instruction until the data is actually ready. It turns out that in this case, we have to delay it by 2 clock cycles, not even 1. And if we do that, then really in this, right, so I will call this, T1, not, we only fetch the instruction for the first instruction. T2, we decode and read registers for the first instruction. Nothing happens with the second. T3, we execute the first instruction. Execute means we are adding the contents that we read from T0 from the contents that we read from T1. Memory is T4, and it's not used for the R-type instruction, which is add. So that's why you see it's not grayed, because it's not used in this for this instruction. Okay. Whereas EX, see how it is grayed, because this is their hardware component that is used for this instruction. And so now in T4, we can finally start fetching our next instruction so that when T5 comes, the value that add computed will be written to S0 in here between 800 and 900. And then our second instruction will read S0. And since it's a read, it will happen between 900 and 1000, right? So it will be so let me, yeah, so it will be here. It will be red, and that's why it's fine, right? Because we are reading the value that by the time we start reading has already been written. Obviously, we cannot get rid of those bubbles, because then it would mean that we have to read the value that has not been written yet. And that's why it's a data hazard, right? It's a data hazard, not a control hazard, because it has nothing to do with branching. It is purely on the dependency between the data, right? This value written is read here, and we see that with two instructions next to each other, it's just not going to happen. It's not going to work correctly if we didn't delay their second instruction by 2 clock cycles, actually. So what can we do? And this is actually all that you need to know for homework 6, right? Because for homework 6, you need to implement their simulator that shows us how instructions execute. So it essentially shows a stylized diagram, multi-cycle diagram, very similar to the one that we looked at in this slide, except for instead of bubble, you would print an asterisk. Okay, and you don't need to worry about forwarding. So forwarding makes things more complicated, but also more efficient. Again, this is not on homework 6, all right? But we continue our conversation with forwarding, also known as bypassing. This is a way to avoid stalling the pipeline, or at least stalling it by as much as we have to do with no forwarding. So the idea of the forwarding is that, well, the result that we need, we can actually use it before it is even formally written to the register that we need to read. As you know, as long as we know what that value is, we might be able to fast forward it to the correct to the correct part of their instructions. So with following up on our previous example, we don't really have to insist that the value of sum is written to S0, because then it is purely read from S0. If we could somehow take this sum and directly route it to their ALU, right? So to here, without really writing it to S0 formally, just to make sure that sub can proceed and it has the arguments it needs to perform the subtraction. That would solve the problem. This is exactly the idea behind forwarding. We don't wait for their value to be stored in the register. As long as, as soon as we get their value that we want, right, which is going to happen here at time 600, the first instruction will compute the sum, and then we can sort of shortcut this sum into their next instruction so that it knows what to sum, or in this case, subtract. Okay, so then it will solve the problem. Now we no longer need to have bubbles. We no longer have to stall the pipeline. So of course, S0 still needs to be updated. So our first instruction would still need to write back the result into S0, but that that can happen in following the normal course of actions in time period between 800 and 1000, while we are not we're not holding back our sub instruction. Our sub would be able to continue while this, even before the value that first instruction computed is written back to the register file, which we exactly see is going to happen here. Of course, it will require extra connections in the data path, and it will make it more complicated. So this path here is more like a concept, right? Because it's just to make sure we're on the same page. This is the same hardware component. This is the same ALU. It just shows how it is used for different instructions in different time periods, but it's the same component. It's the same hardware thing, and that's why what it means in the actual design, we would have to have a feedback from the output of the ALU to the input of the same ALU. And we are going to talk about next time. Before I let you go, we still have a minute. Let me see what people are saying on their chat. So the value is delivered to the next instruction, then the value is stored in S0. That is exactly correct. Good job. Yep. And all right, wait, so you can have the clock cycle of the writing to S0 and do the reading of both registers at the same time for the sum instruction. How does it work? So we just remember, register file is unique in that it allows reading and writing on multiple addresses at the same time. Okay, and that's why we are able to read one address and write another address. But even if we are talking about their same address, right? It only takes 100 picoseconds following their numbers in our example to read or write a value in the register. So we would be able to read, to write. So imagine this is 100, 200, oops, 200, 300, right? We would be able to write the sum register here and then read that same register here, okay? In it, because it only takes, following our example, 100 picoseconds. So even if it's the same register, it is possible. All right, we are at our time mark, so let's stop here. And is there a specific component that would handle pipelining that is to be added to our diagrams, or is it present already? No, it's coming up. We will get to that in the next lecture, obviously on Friday. But you have everything that you need to know for the homework 6, because homework 6 is no forwarding, so you can definitely start working on it. Do not wait until the Thanksgiving break. All right, so folks, everyone, you have a great day, and hopefully I see all of you, most of you, in our review session at 8 p.m. tonight. And good luck on your test tomorrow. Yeah, I will see you all again on Friday in our lecture. Thank you, everyone. Have a good one.